Covalent bond. So no free electron this time. When you will increase the temperature, this bond will break. Some electron will be there, some free electron will be there, some holes will be there. Due to that, there will be some increase in the electrical conductivity of the intrinsic semiconductor. So you can say due to increase in the temperature, there is some increase in the electrical conductivity of the intrinsic semiconductor. Okay, so the electrical conductivity of the intrinsic semiconductor increases with temperature. Fine. Why increasing? You know, even on reaching the room temperature, its conductivity is very poor. So the conductivity is increasing, but at room temperature, the conductivity is very poor. At room temperature, the conductivity is very poor. Conductivity very poor at room temperature. Okay, so conductivity is low. That is why there is a requirement of the extrinsic semiconductor. And how the extrinsic semiconductor made? Okay, with this idea, if we will add certain impurities, impurities in the intrinsic semiconductor, if we will add certain impurities, then it will increase the conductivity of the intrinsic semiconductor. Okay, it will increase the conductivity of intrinsic semiconductor. If we will add impurities to the intrinsic semiconductor, it will increase the electrical conductivity of intrinsic semiconductor. Nafisa and Matthew, if there is any problem with voice, if it is breaking, okay, if any distortion in voice, then you, it's fine. It's fine, then it's okay. If there is any problem, then you can ask me, okay?
Sure.
Now, third point.
Okay, sir.
So basically, if you are adding the impurity, if you will add the impurity to the intrinsic semiconductor, so the conductivity of that intrinsic semiconductor will increase. Okay. So very small amount in ppm. ppm means parts per million. Parts per million. 1 million is 10 to the power 6. Means, I will tell you, very small amount of impurity atoms can increase conductivity of intrinsic semiconductor many times. Very small amount of impurity, if you are adding in the intrinsic semiconductor, means if you are adding one atom out of 10 to the power 6 or 10 to the power 8 atom, 10 to the power 8 atom of the intrinsic semiconductor, and one atom of impurity, if you will add in this ratio, if you will add, then it is found that the conductivity of a semiconductor will increase almost 16 times. One atom of impurity in 10 to the power 8 pure atoms of germanium increases the conductivity of pure germanium 16 times. Okay. Fourth point. Okay, so now come to the definition. What is the extrinsic semiconductor? So the semiconductor obtained after adding impurity to pure semiconductor is extrinsic semiconductor. So suppose this is the intrinsic semiconductor, you are adding the impurity, now it is a extrinsic semiconductor, and extrinsic semiconductor will have large conductivity. Fourth point. And now the process of addition of impurities intentionally is called doping. The addition of impurities is called doping. The impurity atom is called dopant. The impure semiconductor thus formed is called dopant semiconductor. So extrinsic semiconductor is also known as dopant semiconductor. Okay, now we will discuss the methods of doping. Doping means adding somehow adding the impurity. Impurity means we will add some atoms of different element, some atom of same element. We will use pentavalent impurity or trivalent impurity. Basically, we have given the name impurity. That is, we cannot say that is impurity. Basically, we are adding some foreign atom. Hmm? But we are saying that impurity because uh, initially there will be only in a silicon crystal, there will be only silicon. Now you are adding some external or foreign atom, so that is why we are calling it as a impurity. Okay, so now I will tell you how we can do the doping. First, you should know what is doping. Doping is adding the impurity atom in the pure semiconductor. So doping can be done in two ways. In many ways doping can be done, but we will discuss the two ways. Heating pure semiconductor in atmosphere of impurity atom so that impurity atom diffuse in pure crystal. Second thing, bombarding pure crystal with ions of impurity atom. First is take the semiconductor, and heat the semiconductor in the atmosphere of impurity atom. Okay, in the atmosphere of impurity atom. Suppose here is the atmosphere of impurity atom in the form of the gas, you can say. And now you are heating the you have this is the pure semiconductor you have, and here this is heated in the atmosphere of the impurity atom. So what will happen? There will be the diffusion will takes place, and impurity atom will will combine with the uh, intrinsic semiconductor. Okay, I will show you how these will combine. Second is bombarding the pure crystal with ion of impurity. So this is the pure crystal and bombard the impurities. So after adding impurities, we will get two types of semiconductor, N type, two types of extrinsic semiconductor, N type and P type. So N type semiconductor we will get when we will add the pentavalent impurity. When we will add pentavalent impurity is added. Pentavalent impurity is added. P type semiconductor we will get when trivalent impurity is added. Trivalent impurity is added. Now, what is pentavalent impurity? What is trivalent impurity? I will tell you later. So basically, we have two types of extrinsic semiconductor. We have two types of extrinsic semiconductor. Number one, N type. Number two, P type. So first, I will discuss N type semiconductor. Then I will discuss P type semiconductor. So come to the N type semiconductor. N type. So N type semiconductor, what we are doing for N type semiconductor? In the pure semiconductor of silicon or germanium, we are adding pentavalent impurity. Okay, so pentavalent impurity atoms. Pentavalent impurity means having 5 valence atoms having 5 valence electron. For example, you can take phosphorus, antimony, indium. Phosphorus, antimony, indium. So pentavalent impurity atom we are adding, and these impurity atom will replaces the pure silicon. Will replaces the pure silicon atom from the crystal. So silicon. Now I am taking the example of silicon. Pure crystal of silicon I will take, and I will add the phosphorus. I will add the phosphorus as an impurity. So the electronic configuration of silicon is this. So in the outermost shell of the silicon, in the valence shell, how many electrons are there? 4 valence electron are there, no? 4 valence electron are there. 4 valence electron. In silicon, 4 valence electron are there. In phosphorus, this is the impurity, na? This is the impurity. So how many valence electron are there? 3 to 5. 5 valence electron are there. That is why we are saying this as a pentavalent impurity, because this pentavalent impurity will have the 5 valence electron. So how this will be added? With this diagram you can see. Silicon, silicon, silicon. Now earlier the structure will be like this. Earlier the crystal will be like this. This is the earlier crystal. This is the pure, okay, this is pure silicon crystal. Pure silicon crystal. So in this pure silicon crystal, we are adding impurities, pentavalent impurities. We are adding pentavalent impurity and we are adding phosphorus. Phosphorus we are adding. So now some of the phosphorus atom will replaces one of the silicon atom or replaces the silicon atom like this. Try to connect. Finally, what you have? You have this. So from here, suppose take this example. From here, the silicon is replaces by phosphorus. Now, this phosphorus is having pentavalent impurity is having 5 valence electron. 5 valence electron. So 4 valence electron of this phosphorus will make the covalent bond with other silicon atom, and there will be one extra free electron. There will be one extra electron. This will be one extra electron. Now you can see this. Step by step the diagram I have drawn. Okay. Now see this picture. Now phosphorus has occupied one of the silicon. This phosphorus is having 5 valence electron. 1, 2, 3, 4. And silicon is having 4 valence electron. So this phosphorus 4 electron of this phosphorus will make covalent bond with other silicons, and there will be one remaining free electron we are getting. So on adding one impurity, one free electron you will get. Now you know what will happen. Number of free electron will increase. This electron is basically, you can say this electron is free electron, obviously. Some energy will be given, and that energy is very less energy, that is I think 0.01%, and that is available at the room temperature. So this electron will move to the conduction band. This electron means the free electrons we are getting due to adding the impurities will move to the conduction band. Now try to imagine what I am saying, conduction band and valence band. I told you now, there is one valence band, there is one conduction band. So when the electron will be in the conduction band, it will conduct, okay, and there will be the free electron in the conduction band. So this free electron will be in the conduction band or will move to the conduction band at room temperature, and the conductivity of the semiconductor will increase. Okay, so now see this theory. I have already written the theory. 4 out of 5 valence electron of phosphorus, I told you, will form the covalent bond with neighboring silicon atom, but fifth electron is nearly free. Fifth electron is nearly free electron. Okay, this is the point. The ionization energy required to free fifth electron. Basically, free fifth electron is approximately free, you can say. It is not free because this electron will be attracted by the nucleus of silicon, phosphorus, silicon. So this electron will be little bit free, means little energy we will give it and it will become free. So the ionization energy required to free fifth valence electron, we are talking about this electron. The ionization energy required to free fifth valence electron is very low, that is 0.01% in case of the germanium and 0.05 electron volt in case of silicon. So here is the silicon. So the energy required will be 0.05 electron volt, contrary to that of required in the pure semiconductor. Okay. So basically in pure semiconductor, what is happening? For the electron to make it free, there is a requirement to break the covalent bond so that the electron will become free in the pure semiconductor and it will move to the conduction band. After that, the conductivity, or after that the conductivity will increase. But here already there is a free electron, almost free electron we have. A very little amount of energy is required to make this electron as free electron. Okay. So in case of the pure semiconductor, understanding na, contrary to the required in pure semiconductor. Okay. So in pure semiconductor, energy is required to break covalent bond to a free electron, and that energy required is basically this germanium. For germanium, 0.72 electron volt. For silicon, it is 1.1 electron volt. Okay, 1.1 electron volt, and this much of energy is not available at room temperature. This much of energy is not available at room temperature. So we have to supply some extra energy. Try to connect with me. Okay. So, but this energy will be required at the room temperature. Okay. Now, next point. The energy required to free fifth valence electron can be obtained at room temperature because it is very, very low, 0.01 for germanium, 0.05 for silicon. So this electron is set to free and it goes to the conduction band and it is available for the electrical conduction. So pentavalent impurity donates. So what the pentavalent impurity is doing? Donating one electron per atom, and hence they are called donor impurity. So pentavalent impurity is impurity known as the pentavalent impurity, donor impurity. Pentavalent impurity is a donor impurity because pentavalent impurity is giving one free electron or one electron. So the conductivity will increase. The conductivity increases with doping. Obviously, the conductivity will increases with doping. More doping you will do. More doping you will do. More doping. More doping means more adding of. More doping means more adding of impurity. More donor impurity. More donor impurity. And more free electron. More free electrons. And more free electrons means more conductivity. Now 6 point. Some free electrons are also generated thermally due to the breaking of two covalent bonds. An equal number of holes are also generated. Now, if this will be at room temperature, this process is taking at room temperature. So at room temperature, we know some of the covalent bond will break and some electron will become free, and same number of holes will be also produced. When the electron will break when this bond will be broken. When this bond will break, So electron will become free. Okay, electron will become free, and what will happen? There will be one vacancy created. So basically, due to the room temperature, equal number of electrons are generated and equal number of holes are generated, and that will be very much less as compared to the free electron created by the pentavalent impurity. So some free electrons are also generated thermally due to the breaking of covalent bond, and equal number of holes are also generated. Number of electrons. Now next point. This is very theoretical topic. Okay, so Ne is the number of free electrons per unit volume, and NH is the number of holes per unit volume. So number of electrons per unit volume means number of electrons we will get from where? Number of electrons we will get from the pentavalent impurity. Pentavalent impurity is giving electron. Pentavalent impurity, and some of the electrons we are also getting due to the breaking of covalent bond. Due to breaking of covalent bond at room temperature. So this pentavalent impurity will give more number of electron as compared to the number of electron we will get due to breaking of covalent bond. So this number will be at almost 90%, and this is 10% approximately. So number of holes we are getting, number of holes in this. How we are getting number of holes? When the covalent bond will break, electron will become free, and the electron will create one vacancy, and that vacancy is the number of holes. So number of holes we are getting by breaking of the covalent bond. So due to breaking of covalent bond, due to breaking of covalent bonds. So now you can see here number of electrons are much greater as compared to the number of holes, because pentavalent impurity is giving one extra electron, but holes you are getting due to the room temperature, or due to the breaking of the covalent bonds. So in this case you can say that number of electrons per unit volume will be much greater than the number of holes. So in case of the n-type semiconductor, the majority charge carrier are electrons. So majority charge carrier, the majority charge carrier in n-type are electrons, or you can say free electrons. You can write electrons. Next point, n-type semiconductors are electrically neutral. So n-type semiconductor are electrically neutral. You can see here. This is the phosphorus atom. You have added the phosphorus atom in the silicon, and then you are getting the n-type semiconductor. But one extra electron, this phosphorus atom, this is the phosphorus atom. This phosphorus atom is giving one extra free electron. So why then the n-type semiconductor is electrically neutral? The reason is very simple. This is the phosphorus atom, no? This is the phosphorus atom. So this phosphorus atom, silicon atom is there, na? Silicon atom. So this silicon atom is having atomic number of silicon. Okay, so the silicon number 14, na? Silicon Z is equal to 14. Atomic number 14. So this is having 14 protons and 14 electrons. Phosphorus atomic number 15. So this have the 15 proton and 15 electrons. So basically, when the phosphorus atom is replacing the silicon atom, so this phosphorus atom is also electrically neutral. This phosphorus atom is replacing the silicon atom, but this phosphorus atom is having this free number of electrons in phosphorus atom is 15, and number of protons are also there. So that is why the n-type semiconductor is electrically neutral. So you can write pentavalent impurity, pentavalent impurity brings one extra electron, but it also brings one extra proton. This question they can ask in board exam, very easy question. One extra proton. This phosphorus atom is replacing the, so this phosphorus atom is also electrically neutral. Number of proton in this phosphorus is equal to the number of electrons. Or if this phosphorus is giving one extra electron, so on the same time, at the same time it will give, means we are adding the phosphorus, so we will get one extra proton also. Now energy band for n-type semiconductor. Energy band diagram. So this is very simple. This is the valence band, this is the conduction band. So in n-type semiconductor, electrons are the majority charge carrier. So in conduction band, there are more number of electrons. And in valence band, there are electrons. These are the valence band electrons. And few holes will be there. And this hole is due to that when at room temperature, some of the electron will move from valence band to the conduction band. Okay. And this is the donor level. Donor level means you can say that this is basically the energy level of the electron. Energy level of this electron. Energy level of this electron means this small amount of energy you will give to the electron given by the pentavalent impurity. It will move to the conduction band and take part in the conductivity. And this value is 0.01 electron volt for germanium, and it is 0.05 electron volt for silicon. Okay, and this energy gap is this. Electrons are the majority charge carrier, holes are the minority charge carrier in case of the n-type semiconductor. Now we will discuss the p-type semiconductor. So in case of the p-type semiconductor, trivalent impurity atoms we will add. So trivalent impurity atoms means barium, aluminium, indium you can take. So with silicon, suppose we are adding aluminium, so this is the electronic configuration. So in the valence shell of aluminium, 3 valence electron are there. Silicon, 4 electrons are there. So what will happen? This aluminium atom, see here, this will be the crystal structure. This is 4 valence electron means silicon, with silicon, 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 and one of the atom of the silicon is replaced by trivalent impurity. This is a trivalent impurity. This will have 3 valence electron. 1, 2, 3. 3 valence electron will be there. So 3 valence electron will be there. So this electron, see in this diagram, it will become clear from this diagram. This is aluminium, is the trivalent impurity. Trivalent impurity. This is the trivalent impurity. So this trivalent impurity will have 3 valence electron, 1, 2, 3. These 3 valence electron will make the covalent bond with the other silicon atom. But there will be one vacancy here. And this is basically the hole. Because this aluminium is having the 3 valence electron. These 3 valence electron will make covalent bond with other silicon atoms. But there will be one vacancy here. Okay. So this is basically the incomplete covalent bond, you can say. And here is one vacancy, and this vacancy is known as the hole. So 3 valence electron of aluminium forms 3 covalent bond. 3 valence electron forming 3 covalent bond, 1, 2, 3. With neighboring silicon atom, a vacancy is left at one side of the trivalent impurity atom. So this is the vacancy left. On application of the electric field, an electron from one covalent bond. Now this is interesting. On application of the electric field, an electron from one covalent bond may jumps to the hole, and a new hole appears at the site of electron. Basically, when you will apply the electric field, see from this figure, when you will apply the electric field, so the neighboring electron, you can say this electron, when you will apply, suppose the electric field like this in the upward direction. So this is the electron, this neighboring electron will jump into the hole, and here a no new hole will be created. So in this way, the holes will be created. So here I have made this. Okay, this is the aluminium having 3 valence electron and one hole is there. So if you will apply the electric field, the electron from the neighboring silicon atom will occupy this hole, and now here will be the new hole, and here covalent bond will form. In this way, there will be the hole generation in case of the p-type semiconductor. So one impurity is giving one hole. You can say one impurity is giving one hole. In case of the n-type, one impurity is giving one free electron. Here, one impurity is giving one hole, and hole is a positive charge. Hole also is a charge carrier, positively charged carrier. Okay. So now, talking about this, the motion of electron from here to here. First, read this. On application of the electric field, an electron from what we should do? We should write this third point. Diagram should be here. So now, second point, on application of the electric field, an electron from one Covalent bond may jump to the hole and a new hole appears at the site of electron. This required means the motion of electron to occupy the hole or energy required by the electron to occupy the hole. We are talking about that. This requires very small amount of energy, approximately this much amount of energy. This energy is available at the room temperature, hence large number of holes are available for electrical conduction, and holes we know are in the valence band. After this, we have this diagram. Okay, but if you will apply the electric field, this electron will move from here to here and occupy this hole, and new hole will created. And for you have to means you can say that for the electron to occupy this hole, a small amount of energy is required. That energy is 0.01 electron volt for germanium and 0.05 electron volt for silicon, and that is available at the room temperature. So large number of holes will be created. Holes will be created in p-type semiconductor. Next point, trivalent impurity. Now, not talking about the impurity. Trivalent impurity accepts one electron, or you can say, it is giving one hole, or it is accepting one electron. Here, what is this? This is the trivalent impurity. Aluminium. Here is the trivalent impurity. Aluminium here is the trivalent impurity. This is accepting one electron. Accepting one electron. Okay. So trivalent impurity accepts an electron. Oh. So trivalent impurity accepts an electron from neighboring atom. See here, accepting one electron from the neighboring atom. Okay. Hence, it is called acceptor impurity. So trivalent impurity is acceptor impurity. The reason is it is accepting one electron from the neighboring atom. The electrical conductivity depends upon the level of doping. So I told you that more will be the doping, more number of holes will be there. Okay. So you can write here more doping means more acceptor type impurities, means more acceptor impurity means more holes. Okay, and more holes means more conductivity. Now, few covalent bonds may break. Few covalent bonds may break, which generates free electrons and equal number of holes So we know that at room temperature, some covalent bond may break. Okay, wait. few covalent bond may few covalent bond may break which generates free electrons and equal number of holes. So holes are also generating due to breaking of covalent bond. So two types of charge carrier we have: holes, number of holes. So holes will be due to trivalent impurity. Trivalent impurity is creating one hole, na? One trivalent impurity. So hole will be due to trivalent impurity, and also the holes will be due to breaking of one covalent bond. Breaking of one covalent bond means electron will become free. It will create a vacancy, and that vacancy is a hole. So breaking of covalent bond. Now electrons will be due to breaking of covalent bond only. Breaking of covalent bond. So now see the energy diagram, energy band diagram. So energy band diagram, this is the valence band, this is the conduction band, this is the energy band gap, this is for germanium, this is for silicon. Now here in this case I told you that holes are the majority charge carrier. Here you can say that number of holes are much greater than number of electrons. So you can say holes are majority charge carriers. Holes are majority charge carriers. Charge carriers. So, and holes are found in the valence band. So here will be more number of holes in the valence band, and few electrons will be there due to this is basically the thermal electron. So you can say free electron due to breaking of bond. And these are the holes due to pentavalent impurity. Due to trivalent impurity. And this is the acceptor label. This is the acceptor label. Acceptor label means at least this much amount of energy is required by the electron so that it can occupy the hole. And when it will occupy, the electron will occupy the hole, new holes will be generated. Okay. After that, we have p-n junction diode. After that, we have p-n junction diode. p-n junction diode is what? See, this is a silicon crystal. This hole is a silicon crystal, and this silicon crystal is doped in such a way that this part is p-type semiconductor, is behaving as p-type semiconductor or acting as p-type semiconductor. This part is acting as n-type semiconductor. So this is p-type semiconductor. One half of the silicon crystal, what we have done, we have taken one silicon crystal and we have doped that silicon crystal in such a way that one half of the silicon crystal is behaving as p-type semiconductor and other half of the silicon crystal is behaving as n-type semiconductor. In p-type semiconductor, holes are more, holes will be majority charge carrier. In n-type semiconductor, electrons. So basically these are electrons and these are holes. So in n-type semiconductor, holes are the majority charge carrier. So you can say more number of electrons here and here more number of holes are there. Now you can see on both sides there are different number of holes. Here electrons are more, here holes are more. Here holes are less, here electrons are less. Means there is a concentration difference of electrons and holes. So what will happen? Due to the concentration difference, the electron will drift. The electron will drift from n side to the p side. The electron will drift from n side to p side, and hole will drift from p side to n side. Hmm? Okay. Again, I am telling. Due to the concentration difference of holes and electrons from the n type will drift towards p type. Holes will drift towards n type. So when one electron will cross this is you can say junction. When one electron will cross this junction, that is known as the diffusion. So when the electron will diffuse here, so that electron is negatively charged. So when the electron will diffuse means crossing this junction, going uh, going to the p type semiconductor, p side. So when electron will go, electron will leave behind the positively charged ions. Electron will leave behind the positively charged ion. So when electron will move from here to here, so here we will have positively charged ions, and when holes will move from here to here, and holes are the positive charge. So when hole will move from here to here, leaving here the negatively charged ions. So basically, this we will get p type, n type, and a layer we will have having positively charged ion and negatively charged ion. And why these positively and negatively charged ions are created? Due to the diffusion of the electron and due to the drift of the electron. And why this is happening? Because of the concentration difference of the electrons and the hole in p side and n side. Now this is theory. When a single crystal of silicon or germanium is doped in such a manner that half portion of it acts as p-type and other half acts as n-type semiconductor, this device is known as the p-n junction diode. So what is p-n junction diode? Now you know. This process involved in the formation of p-n. The process involved in the formation of p-n junction diode are diffusion and drift. Diffusion means when one electron will cross the junction or one hole will cross the junction. Drift means when the electron or hole will move towards the p type. When electron will move towards the p type and when hole will move towards the n type, that will be the drift. Drift mean drift will occur within the region. So if the electron is moving in n region, so that will be known as drift. And if the electron will cross the junction, that will be known as the diffusion. Same is the case for the hole. So due to the concentration difference, the electron will drift from n to p side, leaving behind positively charged ion in n type, and holes will drift from p to n side and leaving behind the negatively charged ion in p side. Okay, negatively charged ion in p side. This is p side, and positively charged ion n side. This will set up a layer of positive and negative ions around the junction, and this layer is called the depletion layer. Okay, so this layer, a layer is formed, and this layer is known as the depletion layer. After that, due to this depletion layer, due to this is the positive charge, this is the negative charge. Due to this depletion layer, there will be a potential difference, and that potential difference is known as the potential barrier. This is the junction. What is this? This is junction. So negative charge, positive charge, and this is a depletion layer, and this you can say this is a negative terminal. This negative charge you can consider as negative terminal. You can consider this as a positive terminal. So it will behave as a cell or a battery is connected like this, and there will be the potential difference. That potential difference will be a potential barrier. Potential barrier. this type of graph we will get initially when you will move from P to N side or from N to P side. So initially the potential will be when suppose the electron is moving from N to P side. So when the electron will move from N to P side, initially the potential will be less, and when it will be near the junction, the potential will be more. Okay, and when it will just about to cross the junction, that will be a potential barrier. Basically, this will be a potential barrier. This will be a potential barrier. So the accumulation of the positive ion in N type and negative ion in P type set up a potential difference across the junction. This potential difference is known as the potential barrier. So the value of the potential barrier uh, is 0.3 volt for germanium, 0.7 volt for silicon. So due to the potential barrier, what will happen? Now a potential barrier is created here. So basically this here a potential barrier is created due to the depletion layer. So now the motion of the electron or drift of the electron or drift and diffusion of the electron will decrease. Or drift or diffusion of the holes also will decrease due to the formation of the depletion layer. Initially there will be the formation of depletion layer, but when the depletion layer will form, the motion of the electron and the hole will stop. Now, due to this potential difference, due to this potential barrier or potential difference uh, in the depletion layer, a potential barrier field is generated. So, what is the barrier field? So, barrier field is the potential difference. You can write the definition of the barrier field. The potential difference set up potential difference or you can say potential barrier. Set up an electric field across junction and this field is called called barrier field. Field is called barrier field. Okay, if you want to find the barrier field, suppose this is EB is the barrier field and potential barrier is VB. If you want to find the EB, it will be VB divided by L. L is the length of depletion layer. Length of depletion layer. Now symbol of the PN junction diode, PN junction diode is this arrow and this is representing the P side. This is representing the P side and this is representing the N side. So basically it will be like this. And one more thing, the direction, or you can say, I will tell you later. So this end is the negatively charged end, na? Here is the negative charge. This will be the case. Oh, I made this wrong. Here will be negative charge. This will be negative charge on P side, positive charge on N side. So it will be negative charge and it will be like this. Okay. So you can represent like this also. Okay. So it is the PN junction diode. PN junction diode. This is negative. This is positive. Now remember this symbol of PN junction diode. We will discuss now forward wise and the reverse wise. So this is the PN junction diode, and just this PN junction for the forward wising. This PN junction diode is connected with the battery. So you can say this is P side, this is N side. We know that P side is negative, N side is positive. So when this is the positive terminal of the battery, this is the negative terminal of the battery. This is the key, and this is rheostat or variable resistance. Okay, this is rheostat. This is rheostat. This is a battery. So when you will connect the positive end of the battery to P side and negative end of the battery to the N side. So this diode is known as the forward wise diode. Okay. So the PN junction is said to be forward wising if the positive terminal of the battery is connected to P side and negative is connected to the N side. So in this case, this is positive, this is negative. So this will be the direction, and this is positive, this is negative. So this is the direction of the electric or field barrier. Okay. So direction of barrier field due to the diode will be in this direction. So you can say direction of potential due to the barrier potential also will be in this direction. And here the direction of the field is from positive to negative. So this is basically the battery. This is basically the battery. So battery means applied voltage will be there here. So applied voltage direction is in this direction, and basically the potential difference is a scalar quantity. But see here the connection. With the help of electric field, we can say the electric field due to the battery will be in this direction, and electric field due to this diode will be in this direction. Okay. So the direction of the you can say the direction of the potential difference due to battery will be in this direction, and the direction of the barrier voltage due to the diode will be in this direction. So net voltage will be V minus VB. V minus VB. So this potential barrier earlier was VB. Now it is V minus VB. It is less than VB. So potential barrier will decrease. So the potential barrier V minus VB decreases across the junction. So across the junction diode, the potential barrier will decrease. Okay, the potential barrier V minus VB. Now the potential barrier is V minus VB. That it decreases across the junction. And when the potential barrier will decrease, means energy barrier will decrease, you can say. And when the energy barrier will decrease, more amount of charge will flow. Okay, the majority charge carrier can flow across the junction now, and resistance across the junction will decrease. And due to that, the diffusion of electrons and holes across junction will take place, and depletion layer thickness will decrease. Okay, why depletion layer thickness will decrease? Because when the electron will move from here to here, when electron will move from here to here. So this positive ion, okay, this, and there is a recombination of this positive ion and the electron. And when the hole will move from here to here, there is a recombination of this hole and negative ion. So due to that, this depletion layer will, the thickness of the depletion layer will decrease. Okay. So due to the diffusion of electron and holes across the junction, the width of the depletion layer decreases as majority charge carrier flow across the junction. Hence, current is in the microampere. Microampere means there will be a significant value of current, you can say, because the thickness of the depletion layer will decrease, and now there will be the flow of majority charge carrier. Due to that, the resistance will decrease and current will increase. So now you can see here, this is the graph, this is the potential, this is the junction, this is the distance. So the new graph will be this. Potential barrier is decreasing now. So potential barrier is decreasing. So earlier the graph was this. This yellow color graph was the earlier graph. Now the potential barrier is decreased to this value, V minus VB. So this is forward biasing, reverse biasing. In case of the reverse biasing, this junction diode is this P side of the junction diode is connected to the negative of the battery, and N side of the diode is connected to the positive end of the battery. So in this case, what will happen? So due to that, what will happen? The potential will be in this direction, barrier potential, and this also, the applied voltage will also be in this direction, positive to negative. So both will add it up, and potential barrier will increase. Potential barrier will increase, and potential barrier will increase means energy will increase. Energy to cross the junction will increase for the charge carrier. Resistance will increase. Current will decrease. So when positive terminal of the battery is connected to the N side and negative is connected to the P side, the PN junction is reverse bias. So potential barrier increases this time. The potential barrier will increase because V plus VB. Okay, it will become V plus VB. Both will be added up. And hence energy barrier increases. So if the energy barrier increases, the majority charge carrier moves away from the junction, and hence the depletion layer increases. Okay, what will happen when the depletion layer thickness will increase? Okay, means what will happen? Potential barrier now will decrease. So due to that, what will happen? Majority charge carrier will not cross the junction. So they will move away from the junction, or you can say they will not cross the junction. So what will they, or you can say they will move away from the junction. So what will happen? Due to that, the depletion layer thickness will increase. Okay, and if the depletion layer thickness will increase, means the resistance will increase, means current will decrease. So resistance across the junction increases. No current flows across the junction due to the majority charge carrier. So due to the majority charge carrier, no current flows due to majority charge carrier. While there are some minority charge carrier which moves across the junction due to the temperature, and hence current is in microampere this time. So very less amount of current will be there initially during reverse bias condition. So in case of the forward biasing, the current was in milliampere, and now the current is in microampere. Milliampere means 10 to the power minus 3 ampere, and 10 to the microampere means 10 to the power minus 6 ampere. Now the potential barrier will increase. So this was the earlier diagram. So finally the potential barrier will become large. V plus VB. V is the applied voltage, VB is the barrier voltage. Okay, so Matthew and Nafisa, please take the screenshots. Today I am very fast. Okay, take the screenshot. And please tell me when completed, okay? Nafisa, are you getting my voice?
Yes, sir.
Please take the screenshots.
Yes, sir. Done.
Okay.
Yes, sir. Done.
Okay.
Done, sir.
Okay. Okay. Do this.
Done, sir.
Okay. Mm. Okay. Take this screenshot.
Done, sir.
Okay. Now take this screenshot.
Done, sir.
Okay. Just a minute. Okay. Now take this screenshot. Okay.
Done, sir.
Okay. Take this. Just a minute.
Done, sir.
Okay. You can only say done. Okay.
Okay.
Mm.
Done.
Okay.
Done.
Okay.
Done.
Okay. So basically, here is the pentavalent impurity, giving one extra electron. Okay. Now p type.
Done.
Okay.
Done.
Okay.
Done.
Okay. Take this screenshot.
Done. Done. Done.
Okay.
Done.
Okay.
Done.
Just wait. No. Okay, so take this screenshot first. Done? Completed, Nafisa?
Yes, sir.
Okay. Now take this screenshot.
Done.
Okay.
Done.
Hmm.
Done. Done.
Okay.
Done. Done. Done.
I have to take one more lecture, I think, of half an hour. Okay, please take the screenshot.
Done. Done.
Hmm.
Done.
Okay. Hmm. Okay, so this is done. So now we have these topics left. VI characteristics of forward bias, VI characteristics of reverse bias, and rectifier, half wave rectifier, full wave rectifier, and filter circuit. So we can finish these topics in half an hour. Uh, I can take 1 hour, half an hour extra now also, and I can finish it. But I think now it will be out of your mind. Okay, I can understand that. So that is why I will take the another. I will finish this in the another class. Okay. So
Okay,
many,
sir.
so much, yeah, so much content is given today because this topic is very theoretical, purely theoretical topic is this. So and some things are experimentally proven in this topic. Okay, so please join the next class. Okay, so
Okay, sir.
I will finish these topics in half an hour to the 45 minutes. Okay, I will finish this topic, and after that we will see. Okay, please join the next class. Okay. Okay.
Okay. Okay, sir.
Okay, so we will meet now in the next class.
Okay, sir. Thank you, sir.
And one more thing, now your exam